everyone, this is Erica. Sorry in advance for messy handwriting, but you gotta admit this is pretty mind-taxing, at least for me. Alright, but good news, part C is the easiest part. So what it reads, make a plot of u of x versus x and identify all equilibrium points. Assume L equals 1.20 meters and K equals 40 newtons per meter. Part D, if the particle is pulled 0.500 meters to the right and then released, what is its speed when it reaches the equilibrium point? X equals 0. Alright, so this is easy. So remember from part B, we got an answer, right? So we're going to use that formula because that's the formula for potential energy in terms of x. It's pretty simple. So we know from part B, that u of x equals kx squared plus 2k L times L minus x squared plus L squared. And guess what? We know what L is. L equals 1.20 meters and K equals 40 newtons meter. Right? So now we're just going to plug that in. So u of x equals 40x squared plus 2 times 40 times 1.2 times 1.2 minus x squared plus 1.2 squared, which we're just going to plug into our calculator. See, this is our potential energy in terms of meters. So what we're going to do is we're just going to plug this into our calculator. So I plugged it into my calculator. This is my formula right here. And so this is x. This is potential energy in the y direction. And this is what you're going to get for your graph. Congratulations. You're done with part C. Oh wait, we need to identify the equilibrium point. So equilibrium point is where force equals 0. Which means that u of x, this one, divided by x must equal 0. Where's that? That's the only point is at 0. That's the only point where the division of u of x divided by x equals 0. So our equilibrium point is 0. Remember, equilibrium is where force equals 0. Simple as that. Alright, now on to our last part. Part D. This is also pretty short. So now the question is asking us to find it when it's 0.500 meters to the right and speed at equilibrium. Question mark? Alright, so this is going to be the conservation of energy. So we know as a particle is moving initially, we have kinetic energy, right? And then there's the potential energy spring. Equals kinetic energy final plus potential energy final. This is our conservation. So initially, at the very beginning, when we're getting ready to ready to release the spring, we know that we have potential energy spring, but we don't have any kinetic energy. This all equals 0, right? And then at final, we know that there's no potential energy spring. It's not connected to the spring anymore. So it's going to equal 0. Simple as that. Alright, so we know that potential energy spring is, if you look at your formula sheet, it's going to equal 1/2 kx squared. So if you plug that in, it should equal 0.400 meters. Let me double check. 40 times 0.5 times 0.5 times 0.5. Well, good enough. Anyway, so it should equal 0.400 joules, which equals the formula for kinetic energy final, which is 1/2 mv squared. At the very beginning of the problem, they gave us a particle that was 1.18 kilograms. So we're just going to plug that in, 1/2 1.18 v squared. So v, we're going to plug that into our trusty calculator, and it's going to give us approximately 0.823 meters per second. And that is our speed at equilibrium, which is where force equals 0. Ta-da! So this wasn't as hard as part A and B, and I hope you understand problem number 49. Good luck!